So let me just start off by saying, does anyone have any particular questions about either of these practice exams? It's okay if you don't. I can sort of look at them kind of, yeah. And whose class are you in? Okay, that's an excellent question. So let's look at, yeah, let's look at some of those questions over here. And I'll look at it this way. So let's just start at the beginning, and we can kind of go back and forth between the two. Although I feel like both of them have similar enough questions that we could probably, there's much to be gained. Also, before I forget, I think it would be a good idea for me to post all of these practice exams in Canvas so that those of you in each class can look at the other ones. Not that they're perfectly going to correspond to what you might be tested on, but it's always good to have more practice. So let's look at these first few problems and kind of see what they're all about. So the first one says, let f of x equal this function when x is less than 3, f of x equal to x squared minus 17 sine of blah, blah, blah for x bigger than 3. Show that limit exists and compute the limit. Take the limit laws that you are using. All right. So yeah, interesting. I would point out a more typical way of writing this function might be like this. F of x equals 4 cosine of 2 pi x plus 22 when x is less than or equal to 3, and it's equal to x squared minus 17 sine of pi x over 2 when x is greater than 3. And yeah, I feel like I might be in a little bit of the same boat because I don't know exactly how much work he wants us to show. We can certainly look at the solutions that were posted and see, but just going off this, here's where I would start. I would start with the limit from each side. So limit as x approaches 3 from the left of f of x. We have to use the left piece, which is the 4 cosine of 2 pi x plus 22. Printing limit as x approaches 3 of 4 cosine of 2 pi x plus 22. And then I feel like it's a little bit of kind of a take your pick. My thought here is I'm going to plug in 3 because that's what we would usually do for a limit. And then I'm going to kind of cite the things afterwards. So if I plug in 3, I'm going to get 4 times cosine of 2 pi times 3 plus 22. Cosine of 6 pi is 1 because it's just 3 full revolutions around the unit circle. 4 times 1 is 4 plus 22 is 26. And what limit laws have we used? A lot of them, really. But I would say overall, we're using what's called the direct substitution property, which is that if you're taking the limit of a continuous function, which this is, we know it's continuous because it's the sum of continuous functions, right? We know cosine's continuous everywhere. We know 22 is continuous everywhere. And if you compose them and sum them, it's still going to be continuous everywhere. So I think it's valid to say this is by the direct substitution property. Although there are probably other things you could say as well. And I think the same thing is true for the other side. If we look at the limit as x approaches 3 from the right of f of x, that's going to be the limit as x approaches 3 of x squared minus 17 sine of pi x over 2. And then that's going to be the limit. Not the limit, I'm going to plug in, sorry, I'm not writing limit anymore. 3 squared is 9, so I'm going to get 9 minus 17 times sine of pi times 3 over 2. Sine of 3 pi over 2 is -1, so we get 9 minus 17 times -1, which is 9 plus 17, which also is 26. Again, by the direct substitution property. And then, since the left-hand limit and the right-hand limit are the same, we can say, great. The limit as x approaches 3 of f of x is equal to 26 because the left-hand limit and the right-hand limit are equal to each other, and they're both 26. Is this enough? I don't actually know.
Is cosine of pi equal to 1?
Correct, yes. Yeah, so right, 6 pi is 3 full revolutions on the unit circle. So we're back on the right side of the unit circle where the x coordinate or the cosine coordinate is equal to +1. So yeah, so here's what I would say about this problem. Maybe you feel like we haven't written enough. Like maybe we need to talk about how like the limit of the sum is the sum of the limits, and the limit of a composition of functions, limit passes through. I would wait to do that until you have time, if you have time, right? Even though you might not feel like you've done enough on this question, you're like, well, I did a decent job. I found limit from both sides. I said something. I'm going to move on to the next question. And if it's a big if I have time at the end of the exam, then I'm going to come back and write more here if I feel like I need to. I am curious, and of course, I don't have Canvas pulled up right here, but I am kind of curious what I did have Canvas pulled up. Let's see. This is for no. Sorry, 1 second. Let's take a look at some files. I think so, yeah. Practice midterms. This was the first one, I think. We'll see. No, nope, this is the still the same idea though, right? So let's see what he just says, I'm just going to list all the rules I used right away. So using the sum rule, the power rule, and the continuity of cosine of 2 pi x, that's how we're getting that the limit of, in this case, x squared plus 18 cosine of 2 pi x, he's just plugging it in. So I feel like you could be kind of scattershot here. Like you say, yeah, these rules, and then do the thing. And you might accidentally list one you didn't use. Probably wouldn't be a crime. So it's not about necessarily doing it exactly right. It's about being efficient and using the time to the best of your ability. We'll do the next one. I feel like he does this next one a different way than I would, which is fine. But, well, it's not fine because he didn't say find the limit. He said, use the factorization trick, meaning he expects you to do it the way that he expects you to, which is kind of annoying, but that's what you got. So, a more typical way of doing this problem, I'll just point out, would just be to multiply the top and bottom by the conjugate. That would totally work just fine. But we're not going to do that here because we were asked to use a factorization trick, which is, I think he likes to factor out the highest power of x that's in the root here. So I believe what's going to happen here is we're going to write this as the limit is x approaches 0 from the right of the square root. I'm going to factor out the x squared that I can inside here. And I have x squared. I can see an interesting alteration on this question. Sorry, x squared times x squared plus 25 minus 5x all over x cubed. We pull out the x squared. What's the square root of x squared? Sometimes it's x. Sometimes it's negative x. In general, it's the absolute value of x. And that's actually not going to matter here, but it will matter in the alternate version of this question that I'm going to ask. So if we did the limit, or we should write this, the limit is x squared to 0 from the right of the absolute value of x times the square root of x squared plus 25 minus 5x all over x cubed. But in this problem, since x is already positive, right, x is on the right side of 0, that means the absolute value of x is equal to just x. And we can factor out an x. So we're going to rewrite this as the limit as x approaches 0 from the right of x multiplied by the square root of x squared plus 25 minus 5x all divided by x cubed. And now we can cancel an x here and an x here. I honestly don't really see the point because we're still going to have to multiply by the conjugate. Because if I plug in 0 at this point, I get 5 minus, oh wait, no, I don't get, sorry, I apologize. I take it back immediately. I was misreading this problem. I thought that was a 5, not a 5x. Oh, but I made a mistake. You guys see my mistake? I know I'm going kind of fast, so it's easy to miss the mistake I made. From this step to this step, I didn't factor the x out from this term here. So that really should just be 5, not 5x. So I take back my take back. Now it is a 0 over 0 type. So we are going to multiply by the conjugate. So again, kind of weird to do all this extra work when we were going to multiply by the conjugate anyway. But okay. So multiplying on the top, let's rewrite it before we multiply by the conjugate here. We've got the limit as x approaches 0 from the right of the square root of x squared plus 25 minus 5 all over x squared Now we multiply by the conjugate, which I probably didn't leave myself enough room for. Squeeze it in, even though it's terrible to do this. Square root of x squared plus 25 plus 5 over the same thing. You know what? That looks kind of small. Let's zoom in a little bit. A little bit bigger. So then, multiplying off the top, we have the limit of x approaches 0 from the right. We have x squared plus 25 minus 25. On the bottom, we have x squared times all that stuff. I'll remind you that when you multiply by the conjugate, you want to multiply out the conjugates, and you don't want to multiply out the things that are not conjugates. Cancel the 25s. X squared divided by x squared is 1. So we're left with the limit as x approaches 0 from the right of x squared, sorry, not x squared, sorry, 1 divided by the square root of x squared plus 25 plus 5. We finally get to plug in 0 and get 1 over 5 plus 5, which is 1/10. And while I don't think all this work was necessary for this problem, I do think it would be necessary if you were taking the limit as x approaches 0 from the left-hand side. Because I will just point out, and I think it would be a real smart question for him to ask on the exam, would be, if you do the limit as x approaches 0 from the left of the same expression, the square root of x to the 4th plus 25x squared minus 5x all over x cubed. Well, when we get to this step here, that ends up being a negative x, and so something totally different happens. In fact, it might not even work out that nicely. No, it still works out okay, right? No, I think it doesn't. Yeah, so this is completely different. So I could see making a case for why you would do that work. I don't, so the reason this is kind of weirdly different is because you end up getting an infinity or negative infinity here because you end up having a division by 0. So be careful. Sure, yeah. So if we just multiply by the, now I'll point out, it's super duper important to read the instructions, right? If the instructions say to do a particular thing a particular way, you should do it that way. But if this one was just the problem given and we weren't asked how to do it other than to find the limit, then I would do it by the following way. The limit as x approaches 0 from the right of the square root of x to the 4th plus 25x squared minus 5x divided by x cubed. And I'm just going to straight off the bat, well, first I'm going to do what? I'm going to plug it in. I'm going to think about plugging it in. If I plugged in 0, I would get 0 minus 0 over 0. So it's a 0 over 0 type. But we should always in the back of our mind be like, can I plug it in and get a number? Okay, I got 0 over 0. Now I'll do the usual steps. In this case, the usual steps being multiplying by the conjugate. The square root of x to the 4th plus 25x squared plus 5x divided by the same amount or expression. As usual, when we multiply by the conjugate, we multiply out the tops, and it's always going to be the first thing squared. So that's going to be x to the 4th plus 25x squared minus the second thing squared, which is 5x quantity squared or 25x squared, divided by x cubed times. So looking at this now, I kind of see why you might need to do what you did. Okay, that's fair. So looking at this, if we simplify the top, the 25x squareds cancel. We're left with the limit as x approaches 0 from the right of x to the 4th over x cubed times the square root of x to the 4th plus 25x squared plus 5x. And then we can cancel an x cubed, and we're left with the limit as x approaches 0 from the right of x divided by the square root of x to the 4th plus 25x squared plus 5x. So I was wrong. You do have to do the work that you did to kind of get there. We can do it at this point though. So let's do it now. So now I'm going to factor out an x squared from inside that square root. So we have x squared times x squared plus 25 plus 5x. I will point out the way I know I'm not done yet, right? Because if I try plugging in 0, I still get 0 divided by 0. So I still have more work to do. So then the square root of x squared comes out. We have the limit as x approaches 0 from the right of x divided by the square root of x squared is the absolute value of x times the square root of x squared plus 25 plus 5x. And then we'll again observe that the absolute value of x is indeed just equal to x in this particular example, since x is already positive. So then we can factor out an x from the denominator. We have x multiplied by, let's actually factor it out from both pieces. Square root of x squared plus 25 and a plus 5, not a 5x. The x's cancel. Left with the limit as x approaches 0 from the right of 1 over the square root of x squared plus 25 plus 5. And then we plug in 0 and we get 1 over 10 like we did before. So it would actually be valid to do it this way. We're still employing the thing he said to employ at some point in the process. We just didn't do it as the first thing we did. Not a bad problem. Kind of a lot though. I'm just going to keep moving through this practice exam unless someone says something they don't want to see. I think there's some decent problems here. And I feel like Noah's exam is a little less straightforward than Chan. But we'll probably have time to look at some of those. So let's look at the next problem here. Let's keep your pictures in order here. Where's my other paper? Sorry, I'm trying not to lose all my papers, and I think I already lost one. I'll find it. So here's the next problem. Consider the function g of x equal to, oh, I know what it was. I was writing on the practical term. That's where it is. So we have g of x equal to the log of sine of 2 pi x cubed plus pi over 2. Oh, geez, wow. On the interval from 3/4 to the 1/3 power, comma, 5/4 to the 1/3 power. It's a very atypical way of writing where a function is defined. And then we're going to let h of x equal g of x times cosine squared of 1 over x plus 1, as long as x is not equal to 0. Part A, show that g of x is continuous. I would probably amend this to say continuous on the given domain. That seems like a better way of stating it, right? Because we're only given this function on this domain here. All right. So I would point out 2 pi x cubed plus pi over 2 is a polynomial. It's a weird polynomial, right? It's got atypical coefficients, but it's still a polynomial and is therefore continuous everywhere. I don't think you need actually, well, you probably should say that. So it's continuous everywhere. Sine of anything is continuous everywhere. So it's already okay to say that sine of 2 pi x cubed plus pi over 2 being composition of continuous functions is also continuous. Is continuous as a composition of continuous functions. Now, the logarithmic function is not continuous everywhere because it's not defined everywhere. So we have to ask ourselves, or really we need to think about the fact that it's not defined when the input is less than or equal to 0. So we just need to kind of double check that this expression isn't going to be less than or equal to 0 on this interval, which is kind of, but we can do it. So if we look at sine of 2 pi times 3/4 to the 1/3 cubed, aka 3/4, plus pi over 2, is annoying is equal to sine of, let's see, 3 pi over 2 plus pi over 2 is 2 pi. Is that right? 3 pi over 2 plus pi over 2? I don't know. It's not including that. Okay, we're okay. Which is 0. That's okay because we're not actually getting 0 because that's the lower left end of our interval of definition here. And if we plug in the other value, sine of 2 pi times 5 over 4 to the 1/3 cubed plus pi over 2 is sine of, let's see, 5 pi over 2 plus pi over 2 is 3 pi, which is also 0. But between 2 pi and 3 pi, sine is never equal to 0. So what I want to point out here is that for values of x in the interval 3/4 to the 1/3, comma 5/4 to the 1/3, two pi x cubed plus pi over 2 is always between 2 pi and 3 pi. Which means that sine is going to be always greater than 0. I should say, or sine of that. So sine of 2 pi x cubed plus pi over 2 is going to be greater than 0 on that interval, which is good enough, right? Because now we can say, great, composition of a composition of a composition is continuous, and that function, this logarithmic function, is going to be defined since our input is always going to be positive. So then we can finally say, great, then log of sine of, oh my God, what a terrible problem. 2 pi x cubed plus pi over 2 is continuous on the domain given. I'm not going to write it again because it's a pain in the butt, right? As a composition of a composition. Kind of a lot. Okay, so being a lot or not, you gotta prepare for it, right? Like this is clear. I mean, the other practice exam I think you gave was similar in content and length. So if you're in nose class, you know what you're looking at. Pun intended. Wasn't very good. All right, second part here. Use the sandwich theorem and the theorem of the limits of continuous functions to compute the limit as x approaches 0 of h of x. So they want us to find the limit as h approaches 0 of g of x cosine squared of 1 over x plus 1, where g was the previous function. So that's going to be the limit as h approaches 0 of grossness log of sine of 2 pi that cubed plus pi over 2. 1, 2, 3. Okay, but here's the deal. Once we figure out what this inner part is doing, we can just plug that into the value because as the question says, we're going to use the fact that the theorem of the limit of continuous functions, meaning if you have the limit of a function and all the functions are continuous, you need to take the limit of the inside part. Or I like to think of it as the limit kind of passing through the function to the inside. So we can really think of this as, and I wrote h approaches 0. I'm sorry, that's x approaches 0. So we can really think of this as the limit as x approaches 0. Sorry, I didn't want to write the limit first. Apologies. This is the log of the sine of 2 pi times the limit as x approaches 0 of the thing we're inputting, which is our x cosine squared of 1 over x plus 1 cubed plus pi over 2. That's what he's wanting you to do, is to say, okay, yeah, that limit, as long as the limit of a continuous function, that limit can pass through to the inside part, and we can take the limit of this part. So then we just need to know, okay, great. What is the limit as x approaches 0 of x cosine squared of 1 over x plus 1? Well, the problem also tells us what to do. It says use the sandwich theorem or the squeeze theorem, whatever you want to call it. So I'm going to start with wherever I start when I know I'm supposed to use the squeeze theorem and there's a sine or a cosine involved. We know that cosine or cosine squared of anything is less than or equal to what? And it's bigger than or equal to what? You could say two different answers that would be correct. You could either say -1. I'm going to go a little bit more refined though and say 0 because since it's cosine squared, it's always non-negative. But if it was just cosine of 1 over x, we take between -1 and 1. And then, so let's say 0 though. And then our job after we write this inequality is to make the middle part look like the thing we're trying to take the limit of. So first I'm going to multiply everything by x. So 0 times x is 0. X times cosine squared of 1 over x is less than or equal to x. And I'm going to add 1 to everything. So 0 plus 1 is 1, less than or equal to x cosine squared of 1 over x plus 1, less than or equal to x plus 1. And then we're going to take the limit of the outer parts. So the limit as x approaches 0 of 1 is 1. The limit as x approaches 0 of x plus 1 is also 1. And so by the sandwich theorem, the middle part's limit also has to be equal to 1. So by the sandwich theorem, the limit as x approaches 0 of x cosine squared of 1 over x plus 1 is equal to 1. And then we can say, great, that means this whole thing is equal to whatever terrible thing it's equal to. It's going to be equal to the log of the sine of 2 pi times 1 cubed plus pi over 2. What comes up with this stuff? And then that's going to be, let's see, 2 pi times 1 is 2 pi plus pi over 2. So we're up at the top part of the unit circle where sine of that is equal to 1. So we're going to get log of sine of 5 pi over 2, which is equal to log of 1, which is equal to 0. All that work for nothing. Not really. So it looks like there's going to be a lot of writing on this exam, right? Not just of math, but of like kind of saying things, making sure you're applying things correctly. What is this next? Find the value of A. Like, what is it? Sorry, there's another part of this question here that says find the value of A making the function Ka of x equal to h squared of x for x not equal. Okay, let's take a look at the next part here. This seems extra funky. So here's what we want to do. We want to find A that makes, and I'm going to write this in the more standard way, Ka of x, which is equal to the piecewise function, h squared of x when x is not equal to 0, and A when x is equal to 0, continuous. Okay, I think that's not as terrible as it sounds, maybe. What does he mean by h squared? So what is h squared of x? Well, it's what it sounds like it is. It's the function squared. So it's h of x quantity squared, which is g of terribleness squared. Okay, so the question we're really asking here is, what's the limit as x approaches 0 of h squared? I think we kind of already figured that out. Because, well, in fact, so here's where, so this is a question. Okay, I see where he's going with this. He's trying to get you to use more of the limit laws without directly telling you to use more of the limit laws. So he's asking you to find, because if you're trying to make this function continuous, right, we need the limit as x approaches 0 of Ka of x, which is the limit as x approaches 0 of h squared of x. We want that to equal h of 0, or sorry, Ka of 0. We need Oh shoot, I forgot to plug it in. No. No, I did plug it in. Are you, what's, okay, that's concerning. 1 second. Am I not powered here? That's, we really don't want to lose power. That'd be terrible. Nope. Sorry, apparently these outlets are. Okay, fine. I feel like it's never been a problem before. Sorry, 1 second. Well, we can stretch it over here. Is it gonna make it? Success. Cool. All right. Sorry about that. So we need this to equal KA of 0, which would just be whatever a squared of 0 was. But we're going to define that to be, no, not a, sorry, just a. Okay, but this limit isn't that bad. We already know what it is, really. We found it in the previous problem. We found the limit as x approaches 0 of h of x. That was what we did the whole squeeze theorem for, right? And we ended up getting 1. So limit as x goes to 0 of h of x squared is the limit as x goes to 0 of h of x times h of x. And since we can write the limit of a product as the product of the limits, which is going to be 1 times 1, which is 1. So then the function needs to be defined to be equal to 1 when x is 0. Oops, sorry. Papers. Does it get better? Yeah. So it looks like the first couple pages are the most awful pages on this practice exam. And it feels like after the first couple pages, it gets a little bit less terrible. So let's look at the less terrible parts of this. Solve the following problems. So the first one is explain why, which means you'll have to write some words. Explain why f of x equal to sine of 1 over x squared doesn't have a limit as x approaches 0. So I think all you really have to say here is that it's going to oscillate infinitely between -1 and 1 as you get closer and closer to 0. If you want to be a little bit more specific, you could point out, and it's kind of super annoying with this stuff, that for values of x that are like the square root of, oh, that's really terrible, yeah, 2 over 3 pi, or the square root of 2 over 5 pi, or the square root of 2 over an odd multiple of pi, which is getting closer and closer to 0. If you plug that into this function, you get values that are 1 and -1 and 1 and -1 and 1 and -1 forever and ever and ever. Now, I wouldn't expect you to come up with that, but I'm just pointing out that there's an actual reason we can state. So if I was asking a more normal question, let me finish writing this here first. So I'll point out that if you plug this in, sine of 1 over that number squared is sine of 1 over 2 over 3 pi, which is sine of 3 pi over 2, which is -1. So the point here is that we found an infinite number of points getting closer and closer to 0, where the y values or the output values go back and forth between -1 and 1 and -1 and 1. Right, if you plug this one in, you're going to get f equal to -1. You plug this one in, you're going to get f equal to +1, -1, and so on and so on and so on. I don't think you need to say all that, but it's good to have an idea of like, oh yeah, this is what's really happening. The function's just going back and forth, back and forth, back and forth as we get closer and closer to 0. So infinitely oscillating with function values between -1 and 1. Let's look at the next one. I'm curious if he's taught this class before. Compute the following limit. Okay. Limit as x goes to infinity of x to the 7/8 plus x to the 3/2 plus x to the -4/3 divided by 3x to the 5/6 plus x to the 9/12. Why wouldn't you reduce that fraction? So the way I would suggest doing this is to, so there's a couple ways to say this. One way to do this is to divide everything by the highest power of x in the denominator. What's bigger, 5/6 or 9/12? Right, 5/6 is equal to 10/12. So one way to go about this is, and again, I don't know if I actually recommend this because it seems like kind of a pain in the butt, but if you divide each term by x to the 5/6, it's going to be kind of gross. So you have x to the 7/8 over x to the 5/6 plus x to the 3/2 over x to the 5/6 plus x to the -4/3 over x to the 5/6. And the bottom, I'm just going to make it a little bit easier. 3 plus x to the 9/12 over x to the 5/6. And in this case, yeah, this seems like I feel like this problem was written expressly in a way to make it hard to do it the way that we often do this kind of problem. 7/8 minus 5/6 is positive. It's going to be 42 minus 40. It's going to be 2/8 or 1/4. Yeah, right. Wow, yeah. 7/8 minus 5/6 is going to be 42 over 48 minus 40 over 48. Just 2 over 8. 2 over 48. Sorry. Which part? Sure. So yeah, so this seems kind of terrible. And then doing the same sort of thing here, 3/2 minus 5/6 is 9/6 minus 5/6, so 4/6. And then something here, you get x to some negative power, -8/6, yeah, -13/6. Down here, you get 3 plus, and then you have 9/12 minus 10/12 is x to the -1/12. So these two things are going where? As x gets really, really big, x to a positive power still gets really, really big. So what we have here is infinity on top and 3 on the bottom, which goes to infinity. The reason I point this out is because, and this is actually really the point I want to make, is it's important to follow the instructions. I did it the way I wanted to do it, and I regretted it, right? This is what I would usually do. Normally the powers would be nicer, like positive integers, and we just divide by the thing. But here, he clearly wants you to do it the way he wants you to do it. So what he wanted you to do is say, well, if I look at this limit here, what matters is really only the highest power of x in each of the numerator and the denominator. So what we can kind of say here is that this is essentially the same as the limit as x goes to infinity of x to the 7/8 over 3x to the 5/6. And doing what he's asking us to do, I would say that x to the 7/8 dominates the numerator. Oh, I'm missing something. Am I right? You guys want to tell me I'm wrong? You guys can tell me. So this is a quick aside here. In case you haven't noticed, I occasionally make mistakes, maybe more than a little bit. So if you see me doing something wrong, don't hesitate to be like, hey, James, I think you made an error. Because sometimes you just get caught up in your own thinking, you're like, hey, that's what you do. Often, typically, people write the term with x to the highest power first. We didn't do that here. The higher power is clearly what? The one that's bigger than 1, right? Not the 7/8, the 3/2. So this is not what we want. So we should say that, hey, this is really more comparable, or we should be thinking about the fact that we have x to the 3/2 over x to the 5/6. So we should be saying, hey, look, x to the 3/2 dominates the numerator. and x to the 5/6 dominates the denominator. And then if we actually calculate this limit, well, if we subtract those powers, 3/2 minus 5/6 is 9/6 minus 5/6, which is 4/6. So end up with the limit as x goes to infinity of x to the 4/6, which is going to be infinity. It would also be appropriate to say the limit does not exist here. We're not getting close to any one particular value, but usually you want to say what kind of infinity you might be going towards if it is correct to do so. Yeah. Okay. Let's look at this next one. So he's telling us to use a fact we know. Use the fact that the limit as x approaches 0 of sine of x over x equal to 1 to help us compute the limit as x approaches negative infinity of 2 plus 4e to the x minus 5x squared times sine of 1 over x squared. Here's what I want you to see. 1 over x squared, as x goes to negative infinity, 1 over x squared is getting closer and closer to 0. So we have sine of something going to 0, which is what we need for this kind of limit to be applicable here. Right? We need the limit as something approaches 0 of sine of that something over the same exact something. So what we really need here is sine of 1 over x squared divided by 1 over x squared. And we have it, it's just not written that way. So we're going to rewrite this. I'm actually going to do two things. I'm going to rewrite it as limit as x goes to negative infinity of 2 plus 4 divided by e to the negative x minus 5 times sine of 1 over x squared over 1 over x squared. And I have a feeling that it would really be appreciated if we showed a lot of steps here. So even though I would probably just like say this is 2 plus 0 minus 5 times 1, I imagine he might like you to do something like this and break it up as, oh yeah, the limit of the sum of things is the sum of the limits. So the limit as x goes to negative infinity of 2 plus the limit as x goes to negative infinity of 4 over e to the negative x minus the limit as x goes to negative infinity of 5 times sine of 1 over x squared over 1 over x squared. And then the limit of a constant is just the constant. E to the negative x, well, e to the negative infinity is e to the infinity, which is a really, really big number, and 4 divided by a really, really big number is a really, really small number. Minus, we can probably bring this 5 out in front of the limit here. And then I think it's okay to just say this limit's equal to 1, 5 times 1. But if you wanted to do more work, which I don't really want to, because I have a limited amount of time to take this test. If I wanted to show more work, I could say, well, we're going to let, I think you can do like a u substitution kind of thing, where you say let u equal 1 over x squared. Then if x goes to negative infinity, u goes to 0. So we can rewrite this as the limit as u approaches 0 of sine of u over u, which does end up being 1. I don't know if you want to do that or not. I feel like I saw that in some sort of solution somewhere, so I could be mistaken, though. I see a lot of math things. So this is going to be 2 plus 0 minus 5, which is negative 3. So nose test is on Friday. You got some time to practice, right? Practice, practice, practice. Practice till your head hurts, and then take a break, and then practice some more. The last page. No, there's one more page. True or false? True or false? The bane of many students' existence, in my opinion. But let's take a look at these. For each of the sentences below, circle whether they are true or false. Use the fact that the limit of x goes to 0, sine of x over x equals 1, if necessary. You do not need to justify your answer, which always feels like a lie, but okay. So let f of x equal x squared minus 1 for x less than 1, and f of x equal to log of 2 minus x for x bigger than or equal to 1. Then f is continuous. So technically, you don't need to show any work here. So if we just think about plugging in 1 for each side, if I plug in 1 here, 1 minus 1 is 0. If I plug in 1 here, 2 minus 1 is 1, and log of 1 is also 0. So it looks like it's true. That would make me feel uneasy if I didn't show any work on the exam, even though the problem says, yeah, I feel like that's not what you really mean. So I would maybe think about the fact that, yes, I know that f of 1 is equal to log of 2 minus 1, which is 1, sorry, which is log of 1, which is 0, and then the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right are both equal to 0. Oh, no, 1, sorry, 1. It feels a little dicey. But that's the idea here, that if you're given a piecewise function like this, you're meant to check the two-sided limits, make sure they're the same. Also make sure it's what the function is equal to. Again, not a great way of writing a piecewise function, but clearly that's how he's going to write it. So get used to it. Next one. F of x equal to cosine of 1 over x squared. F has a limit at x equal to 0. We've already kind of seen that wasn't true in the previous example with the sine of 1 over x squared. Same kind of deal here. This one does not have a limit as x approaches 0 because you get this infinite oscillation thing. I do think it's worth seeing that just in case you don't know. Take your time, sure, yeah. Okay. Here's what cosine of 1 over x squared looks like. Right, you've got this just infinite oscillation here, right? It's just like a block of back and forth, back and forth, back and forth, back and forth. So clearly not getting close to any one particular value. Go away. Okay. Let f of x equal negative 1 over x to the 4th sine 1 over x cubed. Something I will point out here. None of these questions should be left blank. If you have a minute left at the end of the class, circle a bunch of them, right? Circle all true, circle all false, right? If you get to this page, you have very little time. Make sure you've answered each one of these by at least circle something. Because again, if you circle the right one and it says you don't have to show any work, does it actually say that? So you don't have to justify your answer, which I guess is a slightly different statement, but still, you might as well circle something. True story. So looking here, the limit as x approaches 0, yeesh. I don't love this at all. Of negative 1 over x to the 4th sine of 1 over x cubed. Yeah, I don't know. Thoughts? Suggestions? It feels squeezed there to me, but not really. Going false. I don't actually know. I think it's false, but I don't really have a good intuition here. Does anyone have a suggestion? I mean, right, this thing is doing the infinite oscillation BS. And then depending on which side you pick, this thing is either getting close to, nope, it's always going to be going to negative infinity. But the problem here is you've got this thing that's going towards negative infinity, because it's negative 1 over a positive small number. So this is going to negative infinity. But the problem here is that this is bouncing back and forth between 1 and negative 1. So you're probably not just going towards negative infinity. I have a great idea. Let's graph it. Let's see what happens if we graph it. I'm pretty sure it's false, but let's see. So we have, what is this terrible thing? Negative 1 over x to the 4th times sine of 1 over x cubed. Yeah. Yep. Exactly what I thought. It's doing this infinite oscillation thing, but oscillating between positive and negative infinity, which feels worse. Again, this is a great time to point out that we didn't have to justify our work, so great. Pretty sure it's false. I picked false. It's also important to be efficient with your time, right? You only have, what, 50 minutes to take this test? So if you get stuck somewhere, don't get stuck somewhere, move on to the next thing. If you have time, come back. Let's look at this next one here. This one, limit x goes to infinity of x squared sine of 1 over x squared. I feel like we almost already did this one, right? We could say this is exactly the limit as x goes to infinity of sine of 1 over x squared over 1 over x squared. Is it sine of something over the same something? Is the something, not the x, but is the something getting closer and closer to 0? And we're good to go. That limit is 1. That's a false statement. Lastly, this. Suppose f as a function such that the limit as x goes to either infinity or negative infinity of f of x exists. Then there exists an n bigger than 0 such that f of x is less than n for all x. No, it's false. Here's a perfect example of why it's false. F of x equals 1 over x. Think about this. What's the limit as x goes to infinity? Everybody. Well, it doesn't sound like everybody, but yes, it is 0. How about the limit as x goes to negative infinity of 1 over x? It's 0. Is it true? So what does this really say? Is there a number so that the function is always less than or equal to that number? Absolutely not. This function has a vertical asymptote. It gets as big or as negatively big as you want it to. So just because the ends of a function are getting close to some particular y value, it does not say anything about what's happening in the middle. Yeah. Yeah. If he had been more restrictive about what x could be, then it might have been true, but it is not true. It's definitely false. All right. So I know we got caught looking at the no one. Let's look at the other one. Oh, yeah, I said the thing about having a doctor's appointment, right? Yes, sorry. Say a lot of things to a lot of people. So I'll point out there is another practice exam from No. If you're in his class, you should definitely give that one a shot. I would, if I were a student, I would try to actually take it like an actual exam. Sit down, give myself 50 minutes. I imagine you don't get calculators. So pencil, paper, 50 minutes, no distractions. Take it like an actual test, and then go look at the solutions. If you haven't already. If you have already, still take it like an actual test. All right, let's look at this other exam from Chan that looks, I'm not going to lie, slightly more reasonable. So also just good to note that different instructors give different exams, and that might inform your choice of 21B instructor next quarter. So, but it's too late now to do anything about it, so got what you got. Let's look at this question. Find the domain, range, and inverse of y equal to the natural log of x minus 2 over x plus 1. Let's start with the domain. So for the domain, we know that the insides of this logarithm have to be greater than 0. So we need that x minus 2 over x plus 1 is greater than 0. And we also need that x is not equal to negative 1, which probably is just going to fall right out, but just feels good to say it anyway. X not equal to negative 1. The best way to deal with this inequality is to identify the values of x that make this expression either equal to 0 or undefined. It's already essentially factored for us. So I'm thinking x equal to positive 2, x equal to negative 1. I already know I don't want negative 1. I also don't want positive 2. Because if I get positive 2, 2 minus 2 divided by 3 is going to be 0, and the log of 0 is undefined. So I don't want 2 either. And then I pick numbers in each of my subintervals to figure out if the whole thing's positive or negative. Pick something like 3, positive, positive, positive. Pick something between negative 1 and 2, like 0, negative, positive is negative. Pick something less than negative 1, like negative 5, negative, negative, positive. So my domain here is looking like everything from negative infinity to negative 1, exclusive, union 2 to infinity, exclusive. We shouldn't think about finding the range until after we found the inverse function. I should say, if you're asked to find the inverse, we should definitely use the inverse to find the range. So I like to do it slightly differently. I think your instructor likes to solve for x first and then switch x and y. I like to switch x and y first and then solve for y. Either way is fine. So finding the inverse, we have x equal to the natural log of y minus 2 over y plus 1. We do have to be able to go from this logarithmic expression to an exponential expression. So we know our base is e, our power is x, and it's equal to y minus 2 over y plus 1. Excuse me. Multiply both sides by y plus 1. We have y plus 1 times e to the x equal to y minus 2. What's our goal here? We get y by itself, right? Which means we need all the y terms on one side, which means we have to distribute the e to the x before we can do that. So we have y times e to the x plus 1 times e to the x equal to y minus 2. And we want this y and this y on the same side. It doesn't matter which side you pick. But if you pick different sides, you might have answers that look slightly different from each other. Totally fine. I'm going to pick the right side for the y's so that more things are positive, but it doesn't really matter. So I have e to the x plus 2 on the left equal to y minus y times e to the x on the right. Factor out a y on the side the y's are on. So you have y times 1 minus e to the x. And finally divide by that to get e to the x plus 2 divided by 1 minus e to the x equal to y, our inverse function. You might, no, I don't even know. So I would say is our inverse. Or you might then say, I'm going to call this f of x. And then I'm going to call this f inverse of x. Sorry, there's too much paper. So now to find the range of the original function, we're going to find the domain of this function. There's only one thing that's not in the domain, the value of x that makes the denominator equal to 0. So we want to exclude where 1 minus e to the x is equal to 0, or where 1 is equal to e to the x, or where x is equal to 0. So our range is all values except for 0. Negative means 0 exclusive, union 0 to infinity. If you look back at the original function, you can justify that to yourself because if I wanted to get 0 as an output, the natural log of what number is equal to 0? Show me on your fingers. Not the midnotes. Yeah, the natural log of 1 is equal to 0. And there's no way that we could ever get this equal to 0 because x minus 2 divided by x plus 1 is never going to be able to equal 1 for any value of x, right? The numerator and the denominator are always going to be different values, and so their quotient will never be equal to 1. So not that you have to check that, but it's kind of see, oh yeah, that makes sense that we wouldn't get 1, or we wouldn't get 0 in our range. All right, let's look at some limits over here. Yeah, still not the nicest looking thing ever. Limit as x approaches 3 of x minus 3 over root x plus 6 over minus root 12 minus x. And if we plug in 3, it's probably going to be 0 over 0. I think it is, right? 0 on top, 3 minus 3 on, yep, 0 over 0. So we're going to multiply by the conjugate. The square root of x plus 6 plus the square root of 12 minus x over the same thing. I'll point out, as I did last time, that the things you multiply out are the actual conjugates. So we're going to multiply out the denominator. We're going to leave the numerator as just x minus 3 times the gross radicals. So we have the limit as x approaches 3. X minus 3 times the square root of x plus 6 plus the square root of 12 minus x. On the bottom, we have root x plus 6 times root x plus 6, which is x plus 6. The middle terms cancel out, which is always what happens. You multiply by the conjugate. And then we have minus, and ooh, this is extremely important here, minus the entire quantity 12 minus x. If you forget this minus sign, or if you forget to distribute this minus sign here, your denominator won't be 0 anymore when you plug in 3. And we haven't canceled anything, so we shouldn't have gotten away from the fact that we still have a 0 over 0. So I'll just say this again. If we simplify this here, we have x minus 3 on top times The radicals, root x plus 6 plus root 12 minus x. On the bottom, 6 minus 12 is negative 6, and x minus x is positive 2x. We have 2x minus 6. If we hadn't distributed the minus sign, our x would have canceled out. And then we would have negative 6 on the bottom. And that seems like a weird jump to get from a 0 over 0 to a not 0 over 0 without having canceled. So you have to cancel something for a 0 over 0. Typically, there's some weird exceptions, but usually that's what we have. I don't want to write this again. So I'm going to be like, hey, I know that 2x minus 6 is really 2 times x minus 3. And that x minus 3 will cancel with that x minus 3. And then we can say we have the limit as x approaches 3 of root x plus 6 plus root 12 minus x all over 2, because there is still a 2 left behind after canceling x minus 3. And now that we've canceled out the problem, we can plug in 3 and get square root of 9 plus the square root of 9 over 2, which is 3 plus 3 over 2, which is 3. I don't love as a final answer, but okay, that's fine. Conjugates, they're your friends. Oof. I don't know about this next thing, though. So the limit as x approaches 2 from the right of the absolute value of 2 minus x times cosecant of x minus 2. Oh, tricky. Okay, cool. So let's notice that we are on the right side of 2. So let me ask you all, is 2 minus x positive or negative? Negative. So then the absolute value of 2 minus x isn't going to be 2 minus x, because that's going to give you a negative result. It's going to be the negative of 2 minus x, because x is larger than 2. And then if you pick a number bigger than 2, like 5, 2 minus 5 is negative 3, and negative 3 is positive 3, so it totally works. Okay, so then here's where we're going to go with this. We're going to replace the opposite value of 2 minus x with negative 2 minus x. And I'm going to rewrite cosecant of x minus 2 as 1 over sine of x minus 2. Okay. Distribute the minus sign here. So I can rewrite this as the limit as x approaches 2 from the right of x minus 2 instead of negative 2 minus x over sine of x minus 2. I feel like you could just say this is equal to 1 at this point, but someone might prefer you to rewrite this as the limit as x approaches 2 from the right of 1 over the reciprocal of all that. Sine of x minus 2 over x minus 2. We have a sine of something over the same something where that something is going to 0. So that's going to be 1 over 1, which is 1. That's kind of tricky. Tricky to get you to see that you have a sine of something over the same something. Moving along. Okay. Find the vertical and horizontal asymptotes of the following function. Yes, yeah, all right. So let's start with the vertical asymptotes. I'm thinking here's what I said. My candidates, which may or may not actually be where they have vertical asymptotes, but my candidates for the vertical asymptotes are the values of x that make the denominator equal to 0. So 9x squared plus 1 is always greater than or equal to 1, but x squared minus 4, if I set that equal to 0, I'm going to get x equal to plus or minus 2. I might factor it, I might not. So these are my potential vertical asymptotes. But the problem is, it might be the case that when you plug in one of these values, you get 0 on top as well. So let's double check. So if I plugged in 2, on top I'm going to get 2 times 8, which is 16, minus 10, plus 1, which is not 0, over 0. Cool. That means I'm going to have a vertical asymptote at 2. So that means yes, vertical asymptote at x equal to positive 2. If I plug in negative 2, I'm probably going to be fine as well, but it's good to check. So f of negative 2, I'm going to get 2 times negative 8, which is negative 16, plus 10, plus 1, also not 0 over 0. So yes, we're good to go. What I want you to be aware of is that, for example, if I gave you this function, the limit, sorry, not the limit. So just as a quick aside here, if I gave you something like x cubed minus 8 over x squared minus 4, this function would have a vertical asymptote at -2, would not have a vertical asymptote at +2. Because when you plug in +2, you don't get not 0 over 0, you get 0 over 0. So typically 0 over 0 doesn't lead to a vertical asymptote. Vertical asymptote often corresponds to not 0 over 0. There's one other special exception. What other kind of function that isn't a fraction has a vertical asymptote? The natural log. Natural log of x or any log has a vertical asymptote at the the y-axis. That's kind of the only function that isn't a quotient that has a vertical asymptote. Every other function that has a vertical asymptote is some sort of being divided by 0. All right, and then horizontal asymptotes, that's when you take the limit as x goes to infinity or negative infinity. And I think we are going to get different things on either side here. Yeah, that's a good question. I don't hate this question. So let's look at the limit as x goes to infinity. So what I would point out for this function explicitly is that that's not going to be enough. Because for this one here, it's written in a way where you actually get, unless I'm mistaken, I'm pretty sure I'm not mistaken though, I think you get a different horizontal asymptote to the left and to the right. And that's pretty often typical when you have like a square root of x squared kind of thing going on. So we're actually going to use that trick or whatever you want to call it, that process that the other instructor kind of mentioned, where you're going to factor out the x squared, although it might seem less interesting or less, it might feel less like that's what you're meant to do here. So looking at this here, I am going to factor an x squared out from the square root, which you might think, James, you can't really do that because they don't have x squared everywhere. I'm still going to do it. So we're going to have the limit as x goes to infinity of 2x cubed minus 5x plus 1 over x squared minus 4 times the square root of x squared times 9 plus 1 over x squared. Seems valid. It is. And then the x squared comes out as the absolute value of x. So we're going to have the limit as x goes to infinity of 2x cubed minus 5x plus 1 over the absolute value of x times x squared minus 4 times the square root of 9 plus 1 over x squared. Okay, let's be smart about this. This is where things are going to diverge. So if I was doing the limit as x goes to negative infinity, something slightly different is going to happen here. Let's write it down. So up here, since x is positive, the absolute value of x is just x. So I'm going to write this as the limit as x goes to infinity of 2x cubed minus 5x plus 1 over x times x squared minus 4 is, sorry, that times the square root of 9 plus 1 over x squared. Problem's still kind of annoying, but oh well. I would say here probably, how much work am I trying to show? Not all of it. So here's the work I would probably show. The limit as x goes to infinity of 2x cubed minus 5x plus 1 over x cubed minus 4x. I'm actually going to write this other part over here. Okay, now back to what someone said about comparing the highest powers. Highest power on top and the bottom is the same. So what's the limit of this part going to be? 2. What's the limit of that part going to be? Well, 1 over x squared goes to 0, and you have 1 over the square root of 9, which is 1/3. So you end up getting 2/3. I'm kind of skipping some of the work I would normally show, the work I would do if I was really doing this is I'd probably divide everything by x cubed at that point. So actually I'll show that here. So the only difference here is that in the next step, when we write this out, you get 2x cubed minus 5x plus 1. But now, since x is negative, the absolute value of x is equal to negative x. Yeah, so here's the work I would probably choose to show if it were me, although it feels like a ton of writing. I will just say generally, I'm probably writing too much, right? I'm trying to show you all the steps. You could probably skip some of these steps if you feel comfortable with that. So don't feel like you have to write everything out. Just write enough, which I know enough is like ill-defined, but do your best. So we're gonna have 2x cubed minus 5x plus 1 over negative x cubed plus 4x times the square root of 9 plus 1 over x squared. And then I'm going to divide everything by x cubed. Or I think it's probably easier to say factor out an x cubed. So I factor out x cubed. On top, I have 2 minus 5 over x squared plus 1 over x cubed. If I factor out an x cubed on the bottom, I have a negative 1 plus 4 over x squared. And this just stays as is. When you factor out something from a product of two things, you only factor it out from one piece, right? So I have a product of this times this. I can't factor the x cubed out from both pieces. It only needs to come out from one piece. And then the x cubes cancel. And then we let x go to negative infinity. And we get 2 minus 0 plus 0 over negative 1 plus 0 times the square root of 9, which ends up being 2 divided by negative 3, which is negative 2/3, unlike the previous answer, which was positive 2/3. So this does have two different horizontal asymptotes, which is moderately. That's
and it just like 3x times.
Sure. That is also, that's totally valid. And then you're probably cutting out some of the work that I was showing here for sure. Yeah, so in retrospect, it probably would have been a better call to, instead of factoring out just x squared, to have factored out the 9x squared and to have had a denominator that was like x squared minus 4 times the square root of 9x squared times 1 plus 1 over 9x squared. And then that square root of 9x squared is going to be an absolute value of 3x. Still going to get different things on the other side, but a little bit less for a problem. Right, because I already know that 9x squared is bigger than or equal to 0, and if I add 1, it's going to be bigger than or equal to 1. Yeah, you're right. But usually, yeah, so like this here, we kind of just ignore because we know that 9x squared plus 1 is always going to be greater than or equal to 1. So it's never, that's never going to give us the vertical asymptote. Yeah. All right. Got a few more minutes. Good. A classic question. Find the values of A and B so the function below is continuous at every x. So we need the limits to exist. The function exists everywhere, right? F of -1 is something, f of 0 is something, and they're going to be whatever the limit values are as long as the limits exist here. So let's look at the limits. We need the limit as x approaches -1, which is going to use, from the left, which is going to use this piece, which is just going to be -1 plus a, which is 1 plus a. We need that to equal the limit as x approaches -1 from the right, which is again of this function, which is the limit as x approaches -1 from the right of -ax squared plus b. And if we plug in -1, we get -1 times, negative a times -1 squared plus b, which is just -a plus b. So we need this to equal that, which isn't enough to do anything right now, right? We could manipulate that equation if we really wanted to, but let's go ahead and get more information before we start working with that. So then we also need the limit as x approaches 0 from both sides to be equal to each other. So limit as x approaches 0 from the left, we're using this piece of the function, negative ax squared plus b. Plugging in 0, we're just going to get b. And we need that to equal the limit as x approaches 0 from the right, which is using this piece. Negative bx cubed minus 3x plus 5, which is just 5. Great, we found b. B is 5. And then we can plug that in over here and say, okay, 1 plus a equals negative a plus 5. So 2a equals 5 minus 1. So a is going to have to be 2. Not too terrible as far as things go. And then with the a and b found in part A, show that f of x equals pi has a solution. Okay. Good question. So that's an application of what? Intermediate value theorem. Okay. F of x equals pi has a solution. Oof. Sure. So this, yeah, okay, fine. So this is equal to negative x plus 2. This is equal to negative 2x squared plus 5. And that's equal to negative 5x cubed minus 3x plus 5. Interesting. Sorry about that. I'm curious where we're going to find it. My guess, no, do I have a good guess? Yeah, no, yeah, sure. Okay. So we can probably find it in a couple different places, but I think we're going to find it in this middle section right here. So here's what we're looking at. Good question. So here's what I did without saying any words, which is probably not the best teaching. I looked at plugging in negative 1 and 0 to this piece of the function. If I plug in negative 1, I get negative 2 plus 5, which is 3, which is less than pi. If I plug in 0, I get 0 plus 5, which is 5, which is bigger than pi. So I can see that I'm going from below pi to above pi. So I'm going to point out that f of negative 1, even though it's not defined to be this piece, it's defined to be that piece, it's continuous, so it should be whatever that end value is going to be anyway, which is going to be 3 equals negative 1 plus 2, which is 3. And f of 0 is equal to 0 plus 5, which is 5. Notably, we found these values that made the function continuous. So f of x is continuous. So then by the intermediate value theorem, there must be a number c between negative 1 and 0 such that f of c is equal to any number you want between 3 and 5. Is actually the words I would write. Any number between f of negative 1 equal to 3 and f of 0 equal to 5, specifically pi. Pretty good question. I'm a fan of this. I think it's a well thought out, written, good question. It is 2:30. So we won't get to this last one. Oh, the delta epsilon one. I'm so sad I didn't get to do it. I'm not sad I didn't get to do it. But if you want to see me do that, I'm happy to talk about this question in office hours to have right now or tomorrow. And again, as far as Thursday goes, I will let you know if class is meeting or not. Well, I'll let you know if we're not meeting. Assume we're meeting unless you hear otherwise.